Hey everyone, welcome to one of the first of many A-level physics videos. So, just a quick overview on how these videos are going to work. You may notice that this video is titled something like just mechanics, right? So what I'm going to do, this is kind of an overview video. So what this is going to do, we're going to talk about all of the equations you need, I'll briefly explain them, and then all of the skills you need as well. And what happens is, as we go through the skills, you're going to see an annotation on screen, which will link you to a video that I've made specifically for that kind of subtopic or sub-spec point, okay? So what I want you guys to do is I want you to essentially make a mental note or write this down or have a spreadsheet, whatever, and kind of red, green, and amber all of these different spec points and skills. So for example, if first one here is the SUVAT equations, right? So I'll explain them, and if you're like, ooh, SUVAT, you know what, I do struggle with those a bit, maybe you put amber, and then you can click on the related annotation, which will take you to a video where I do a bunch of practice questions for SUVAT, okay? And again, these questions are going to be from all three major exam boards, so it's OCR, AQA and EdXL, because again, most of them have quite a lot of overlap, okay? So it doesn't really matter which exam board you're doing, and the questions are pretty damn similar. So that's how it's going to work. And just to keep in mind that if you're watching this shortly after I've uploaded it, I haven't recorded all of the videos for mechanics yet. There's going to be quite a few of them are broken up into very small chunks so you can revise exactly what you need to revise, but come back to the video later and it should have a video. So for example, the SUVAT one will come out shortly after this, but for example the ones that are slightly further down, like with momentum, that might take 2 weeks or so. So just give me a bit of time. So hopefully that will make sense, but I'll go through it and we'll keep hitting this. So with the mechanics section, we have, this is the first list of equations that you need to be able to use. So bear in mind, when I say equations needed, I don't mean that these are the ones you have to remember. You might have to remember, and I recommend you look at your formula sheet to see which ones you need to know and which ones they give you. But these are the ones you need to be able to use, okay? So first of all, we have the SUVAT / constant acceleration equations. So this is where you have constant acceleration, which is going to be in most of our mechanics work. But if they ever say about kind of what's a limitation or why might this value not be accurate, the problem is that, and it's always the same thing, it's a 1 mark question, you just say acceleration not constant. So this can be due to anything. So for example, one common example is they drop a ball from 1 meter high, how long does it take to hit the ground? You can use SUVAT to work down. They might say, why wouldn't it be that time? Why might it be slightly longer, for example? And you can say acceleration is not constant. Sometimes they might say, well, why is it not constant? Then you would just say, because air resistance is not taken into account. Simple as, right? So all you need to do for those 1 or 2 mark questions at the end of any SUVAT part is just say acceleration not constant and think about what could cause that. 99% of the time it's things like air resistance or water resistance, something similar to that. Okay? But again, you have the SUVAT questions. You have to be able to rearrange and use these formulas. Again, my general recommendation is to list out the variables you have and the ones you want to know. Remember that initial velocity can be 0. So if they don't give you an initial velocity, but they say it's released from rest, or it starts from rest, accelerates from rest, then u is indeed 0. You should also keep in mind that direction matters because all of these are vectors except time, of course. So if you're saying, for example, I'm dropping the ball, I can say downwards is positive, which means all of my things are positive, all of my variables, but likewise I can get the same answer if I say upwards is positive and everything is negative, for example, the acceleration. The next major equation that you need to be able to use is Newton's second law, which is F equals ma, so that's just force is equal to mass times acceleration. But one thing to definitely note is that this force is actually resultant force. So we'll come on to this a bit with resolving vectors, but you need to actually take the resultant force. So what do I mean by resultant force? Well, let's say we have a box, there's 10 newtons this way, 12 newtons this way. F equals ma wouldn't just apply to one of these forces, it'll apply to the overall force to the right. Okay, so you need to bear that in mind. F equals ma, although it seems like a very easy and simple equation, you're going to be using it a hell of a lot in other kind of chapters in A-level physics. So for example, you can equate that to electrical force or centripetal force or any of these other forces that we have. G equals F over m is essentially F equals ma, but it's when you're dropping something. So when acceleration is just g, which is the gravitational. So grav acceleration. It should also be noted that this is the same as gravitational field strength. And again, this is going to come up a lot more, so something you may notice in this video is that there might be some mechanics that are missing. They're not missing, it's just that most of the A-level physics specifications have a mechanics and a further mechanics section. Further mechanics covering things like resonance, oscillations, gravitational fields and things like that. So just keep that in mind. And again, with gravitational acceleration, it's just F equals ma, but where a is equal to g. And you can work out the field strength of gravitational acceleration, so they might have a setting on Mars or something like that. You know, it takes a certain number of seconds for a ball to drop 2 meters. What is the acceleration? Or what is the gravitational acceleration? W equals mg. This is a fairly easy one that you should hopefully know from GCSE. It's just that the weight, so W is weight, equals mass times the gravitational field strength, right? But you should hopefully really try and not confuse this W with this W. So what I've done to make this a bit easier, and some specifications do it, is instead of putting just W, I put a delta W. I'll come on to what that is in a second. Another super important equation, but again not too tricky, but again you will use it to derive other equations in the future, is P is mv, where P is equal to momentum. And that's going to equal to mass times velocity. It should be noted that with all of these equations, if you have a scalar like mass times a vector like velocity, the overall thing is also a vector. So again, with weight, mass is a scalar, gravitational acceleration is a vector, so weight is a vector, as is momentum. So this has direction. So again, with mechanics, one of the main things to do, and this will actually help you in A-level maths, assuming that you're doing it, is you need to give all of these vectors direction. Okay, so what do I mean by that? Well, let's say I take my ball example from earlier. Right? I'm dropping a ball and it's, let's say, 2 meters high, right? Now, I need to pick a direction because everything has a direction, right? We have acceleration has direction, force has direction, velocity has direction, displacement has direction. That's another key point, right? S is not distance, it's displacement. Okay, so it can be negative, and it just means it's going in the opposite direction to what you said is positive. Now, in most cases where you're dropping something, downwards is going to be positive because it's the easiest thing to do. My personal recommendation is take acceleration to be positive, because acceleration is the one that I see most people mix up the signs with. Okay, so if we say that downwards is positive, right, then that means my acceleration is positive. It also means my final velocity, whatever that is positive. It also means this is positive. But I can also say that the exact opposite is true. I can actually take the complete reverse. Right? So if I said instead that upwards is positive for whatever reason, then all of these are now negative, including the displacement. Now this also means that if I'm working out velocity, it's going to be negative. If I work out displacement, it's going to be negative. So the reason why I'm really hammering this point home is there are times when I'm teaching pupils and the answer will be plus 2.5 meters per second and they got negative 2.5 meters per second and say, why did I get it wrong? You haven't. You've just chosen the other direction as positive, which is completely fine. So if in the mark scheme, a vector is positive and yours is negative, or the vector is negative and yours is positive, you get the full marks, okay? They're not going to penalise you for taking a different direction as positive, okay? It might be harder one way than it is the other way, but it's still a correct answer and it's completely valid. There's nothing wrong with it, okay? Except that it's a bit harder, but that doesn't mean you're wrong. I've gone through that a hell of a lot, so let's move on. Moment. So what is a moment? A moment is a turning force. So again, a good thing to remember is that the units are Newton meters, and it's just equal to force times distance. However, it must be perpendicular. So I won't go into too much detail about what this means because it's going to come up a bit later in the mechanics, in the resolving vectors video. But essentially, if you have, let's say you have a rod, okay, and it's attached as a pivot here, and we have a force that's going downwards, let's say 10 newtons, and let's say, just for ease, this is half a meter, then the turning force, or the moment, is quite easy. It's just 10 times 0.5, you know, get out your calculators, 0.5 Newton meters, right? Now, here's where things can get slightly tricky. I've seen this a lot in AQA specifications and OCR, not so much at Excel, but it can still come up, is what if I have the exact same situation, right? However, the force is actually pushing at an angle. Okay, so let's say it's 30 degrees. I can't, and again, let's say the force is, again, 10 newtons. I don't do 10 times the exact same 0.5. And again, I'm hoping this would make sense in real life as well, right? So think about whenever you turn something, for example, a door handle. You have a door handle here. You push directly down, right, to make it easier. If you try and push at an angle, you have to put in more force to do that. Might not be a great example. I don't know. You probably haven't done this, but if you tighten up nuts or bolts, for example, try pushing the spanner at an angle. It's incredibly hard compared to just pushing it straight down, perpendicular to the wrench, right? Or spanner or whatever you're using. So keep in mind that you do have to resolve them so that they're perpendicular to each other. So in this case, you would take the perpendicular component of the force or the perpendicular component of the length itself. Because again, this x, it's distance, but it is essentially a vector in that sense. So again, that's another somewhat tricky one. But again, not too bad if you're stuck. So again, hopefully in your head, just remember red, green, amber. You don't have to write it down, but it could be a good thing. You can obviously pause the video and ask yourself, okay, am I good with these questions? If you have one of your mock tests back or something, that's also a good way to do it. Now this question here, this equation, sorry, is delta W is F delta S. So what this is basically the work done formula, okay? And it just equals force times distance, okay? Now, you might be wondering why there are deltas. Well, deltas normally, well, they don't normally symbolize, they symbolize change in. So this actually reads, change in work done is equal to force times change in displacement, okay? So what that means is it's the amount of energy you put in. So what is work done? Work done is just the energy you put in moving a certain object a certain distance whilst applying a force. So I can apply 1 newtons of force to move it 1 meter. That will give me 1 joule of energy. Or I can put in 2 newtons of force and move it 1 meter, and that's twice as much energy, which hopefully should make sense. I'm pushing it twice as hard. Likewise, if I twice the distance, obviously it's 2 times longer, it should require twice as much energy, right? Again, I like to think about it in terms of myself, right? If I'm dragging something and I increase the distance, I need to put more energy in. Or if I'm dragging it harder, so generally if it's heavier, then I need to put more energy in. So that's how I kind of word things. Next two should be extremely, hopefully, familiar with you. So the first one is the kinetic energy expression. M is mass, and V is velocity. Now, you might be thinking something quite clever at the moment, and that's V is a vector, right? That's correct, but energy is not a vector. So what's happening here? Well, if you square a vector, you're essentially taking the magnitude of it, so it stops being a vector. So V is a vector, but V squared isn't. So you have a scalar times a scalar, which is a scalar. So, slightly interesting there, but yeah. Again, that should be fairly self-explanatory, shouldn't be too bad. Conservation of energy is a really big thing in A-level physics, so being able to equate various different energies to each other is something you have to do. But honestly, half mv squared, you're going to know that like the back of your hand by the end of the course. Next one is gravitational potential energy, which is just going to be m is once again mass. G is, I'm going to call it gravitational field strength in this case because that's a bit more realistic. It's not really to do with the acceleration. And delta H is change in height, or not really a displacement. It actually has to be change in height. So it needs to be perpendicular to the field, right? Like, if I'm standing on Earth and I move left and right, I don't increase my gravitational potential energy, but if I change how high I am, like jump up, I do change the gravitational potential energy. So it's change in height specifically for that one. Then you have power. So power is really important because energy isn't the only thing we care about. We also care about how quickly that energy is released, which is power. And all it is energy over time, or work done over time. So why does that matter? Well, normally P equals E over T is used for things like electrical appliances. So if you have a kettle that heats up water, giving you 10,000 joules, and it does that in 100 seconds, 10,000 divided by 100 is your power. However, you may also have motors, and with motors they don't really provide energy, they provide work done. So you might have, are you ready for this drawing? It's going to be amazing. So you have this motor and it's lifting up some mass through a height, right? And the weight of this, let's make it easy, 1 Newton of weight. And so the work done is going to be, the H, let's say, is 1 meter, is 1 times 1, which is 1. And then if that happens over 10 seconds, then your power is 0.1 watts, right? So that's why there are 2 different equations for it. Work done is when you're kind of moving something a certain distance. Another example they like to use is electric wheelchairs. I know that out of context that doesn't really sound like much, but look, as you do your exam paper practice, you're going to notice they talk about electric wheelchairs and motors a lot. So electric wheelchairs, like they travel a certain distance, you need to work out the energy that is required for that, and then, it takes them 100 seconds. What's the power output? Work done over time. Likewise, they might also give you the power and time and the weight of the person, but then say, okay, so how far did they travel? So you need to be able to rearrange it. So if you remember, work done is force times distance, so it's going to be force times distance over time. So they could give you 3 of these and ask you to work out the 3rd one. So just keep that in mind. Okay, and then lastly, efficiency. So efficiency, you might notice I haven't actually put any values here, any kind of variables. And the reason for that is it can be a bit subjective. So efficiency is useful blank out over total blank in. And then that's what efficiency is, but normally you're talking about percentage efficiency, so you times it by 100 if a percentage, right? So why did I put blank? Well, this can be a few different things. Normally you're going to have energy, right? Normally. So useful energy out. So that can be a bit obscure, right? So you need to really think about what is the point of the thing that we're doing. So let's take an example, right? So we have a kettle and it provides a power output of 100 watts, but only 30 watts is going to heating the water. The efficiency would be 30 watts, the useful stuff, because we want it to heat up, over 100, right? So it's only 30% efficient, right? Because then we times by 100 afterwards. So you need to keep in mind that whenever you're talking about electricity or the electrical appliance, you need to think about what is the useful energy out. If it's a motor, it's motion. Okay, so kinetic energy. If it's a light bulb, it's the light, not the heat or anything else. If it's a kettle, it's not the sound. If it's a speaker, it is the sound. So you need to keep thinking about all these things. And then divide by the total energy in. The other thing that they like to give you instead is power. Right? So again, when we're talking about electrical appliances, we don't normally talk about the energy, right? If I go up to my phone charger, if I look at my phone charger right now, or I look at my kettle or my toaster or my microwave, it tells me the wattage, not the number of joules, right? Because it depends how long you use it for, right? So we normally use power instead. So total power in, this can be a few different things. So it could be the wattage of the actual appliance, right? So maybe a 12 watt or like a 24 watt microwave, and then the amount of power that's actually heating up the, I don't know, ramen that you're eating. Or it could be the actual input power from your socket, right? Because you have 12 volts coming in through your socket. It could be something like that. But yeah, just keep that in mind that it could be any of those. So those are all the equations you need. I actually think that with mechanics, the equations, the only tricky ones are the SUVAT ones. These come with practice, so don't worry, just do a bunch of mechanics questions. Again, if you're doing A-level maths, you're going to 100% remember these, unless you aren't studying at all. So yeah, I think it's quite light because it's mainly about drawing vector diagrams and resolving stuff and doing all that funky business. So, skills needed. You need to be able to draw and interpret displacement time, velocity time, and acceleration time graphs. So, what does this mean? Well, by interpret, they want you to mean what happens if it's a negative gradient, positive gradient, or zero gradient. Okay? So ask yourself those questions. What does it mean if each of these has a negative gradient, a positive gradient, or a zero gradient? So if it's a flat line, right? So the reason why this is really important is a lot of the time, people look at a velocity time graph and see no gradient and then say, oh, the velocity is zero. And then I slap my head really damn hard because it doesn't mean that, it means it's constant. I'm not going to go through the rest because, again, if you're not too sure, check out that video that's appeared on screen right now, you know. Also, just as another aside, is for each of these topics that I go through, the experiments will be a completely separate video. The reason for that is, one, there is so many experiments. For mechanics alone, depending on your exam board, it can be 10 to 14 experiments. It would take way too long. So I'm going to do it in a separate video. And also it tends to be a paper 3 topic, all of the experiments. So I'm going to have an experiment for every experiment video for every single subtopic. So for mechanics, it'll have a mechanics experiment. Every mechanics experiment, no matter what exam board. You should also be able to know how to draw these, of course. You should also know what quantities are given by the gradient. Right? So if I take the gradient of a displacement time graph, what am I getting? What is that number? If I take the gradient of velocity time or acceleration time, does it give me anything at all? Gradient of acceleration time graph, what does it give me? Nothing? Something? What is it? Also, the areas under the graph. So what does the area under an acceleration time graph give me? What does the area under a velocity time graph give me? Ask yourself those questions. Again, the video on screen will go through all of it, so if you have a big question mark, I'm not being mean by not going through it, just go to that video and everything will be fine. That is actually the second point here, so know the physical quantities derived. Keep in mind that it could be none, right? Who knows? So you need to be able to do that. So these first 2 points are the video that's on screen right now. And it's all about different types of graphs. These actually come up a lot more than you think, and it's not as easy as you think, so please, for the love of God, if you're looking at it and saying, easy, GCSE, easy peasy, please actually have a look and be careful because students lose marks on these all the time, even A2 students, okay? It's very easy, they can be very complicated, they can have changing gradients as well. So when I said negative, positive and zero, another thing I should have said is changing gradients. What happens if displacement time graph is an exponential curve or a negative exponential curve? What does that mean? How can I interpret that? Same with velocity and acceleration. What do those things mean? Changing gradients, okay? What happens when it goes to zero, etc. The next major topic, and again, these next 4 points here, so 3 to 7, they're all going to be in one video. So understand and give examples of scalar and vector quantities. Okay, so sometimes multiple choice is quite a big part of your papers. They might say, tick the quantities that are scalars, tick the ones that are vectors. Which ones are vectors and scalars, right? And again, people lose marks on it. You should also be aware that there can be 2-mark questions saying what's the difference between them, give some examples, here's a list of quantities, circle every single one that's a scalar. Okay, so remember, a scalar does not have direction, it only has size. And vectors have size and direction, okay? So keep that in mind. So you need to think about all the different ones and all the different ways that can come about. Okay. Now the next one is probably where things get a bit more funky, a bit more tricky, but again, if you do A-level maths, you have a bit of an advantage because you have to know it for A-level maths as well. You need to be able to resolve vectors into 2 components at right angles to each other by drawing and calculations. So I'm going to draw a little bit. So if we have a vector, generally speaking, it's not going straight to the right, left, up or down. It's going between them, right? It's not just going right, it's not just going up, it's not just going down, it's not just going left, it's between. Right? So you need to be able to break these down into 2 perpendicular components. So I've chosen vertical and horizontal. Can you do that? How comfortable are you? Depends. If you're not comfortable, go to that video right now and then come back to this one. And again, by calculations, it means, okay, you've drawn it. How does that actually affect your numbers? Because again, with physics, physics is just maths that you interpret. So if you're not good at maths, you're going to get good at maths doing A-level physics. And you have to interpret these things. Okay, this one is actually, so this word here, coplanar. So find the resultant of 2 coplanar vectors at any angle to each other by drawing or calculation. So coplanar always confuses students. Coplanar means that they share the same plane. Now a plane, mathematically, is a 2D slice, right? So it has an X and Y. So basically imagine a sheet of paper. That is a plane for our purposes. Now, every single force that we deal with in A-level physics, they're always going to be coplanar. What I mean by this is they're always going to be something, right? For mechanics, okay? They're always going to be acting on the page because that's how we draw them. Now you might have noticed I said that only for mechanics. When you come on to things like electric fields and magnetic fields, there are non-coplanar forces because we deal with 3 dimensions. If that sounds scary, don't worry about it. It's really not that bad. It's okay. It's difficult. It's not bad. But for mechanics, we never really deal with forces that are going perpendicular to the page, right? We don't say, oh, okay, this force is going into the page. So coplanar vectors, it just means that they're acting on this 2D space. They're going left to right, up or down, or some combination. They're not going in and out of the page. So that should make it a bit easier. This thing here, this 0.5, is basically just 0.4. Because remember, when you take resultant forces, all you're doing is adding them up. Okay, so if one goes left, one goes right, then you can add those together. One's negative, one's positive. Add them together. But you need to make sure that they're actually parallel to each other first. So you can't add vectors that are going down and across. You can't add those. Okay, instead we need to add vectors that go parallel to each other. Okay, so you need to go horizontal, add all those up, vertical, add all those up, then take the resultant, then actually take the resultant vector of that force. Which again, if any of that didn't make sense, hop on over to that video that's on the screen. Projectile motion is the next one. I've had a lot of requests for projectile motion, so you should be happy to know that it's the second video I'll be doing, second or third video. Shouldn't be too bad. Actually, third video, the first is SUVAT. But you need to be able to make use of independence of vertical and horizontal motion. So with projectiles, right, they move in a curve, right? So if I throw something, it moves in an arc, okay? So you might think, okay, that's kind of difficult to work mechanically, but it turns out you can treat this direction as completely separate from up and down, right? There's a component that's going straight up and then down, and there's a component that's going to the left or to the right. You can treat them separately, and then the problem becomes a lot easier. It's still complicated because it's basically SUVAT in 2 dimensions rather than the 1 dimension we talk about, which is basically left and right or up and down. So it is a bit more complicated, but again, it's not too bad. I do have a video coming out on that, so just be aware that this is actually a separate video and it should be on screen right now, assuming I've edited it correctly. And lastly, we have for this section, be able to draw and interpret free body diagrams to represent forces on a particle or extend but rigid object. So again, you might have like a box on a floor. You need to be able to label all of the forces on it, and they need to be accurate. So again, this can be 2, 3 or 4 marks depending on how complicated it is. But even more than that, sometimes they give you only 1 mark for the diagram and the next 3 marks are for the calculation. But guess what? If your diagram's wrong, your calculation is all completely wrong. So I know it might seem like a somewhat boring thing to do, and the way I'm going through it in the video is I'm not just going to show you a bunch of situations. I'm actually going to go through exam questions and show you why it matters. Why is it important? But honestly, if these diagrams are wrong, you will get the wrong answer. So you need to be good at doing that. Extended but rigid body, it just means that, let's say this box, it's indestructible, right? Like if I push the top, it's not going to bend, okay, like a real cardboard box will. It's literally a completely indestructible, rigid object, okay? There's no bendiness, there's no squishiness, there's no breakaway bits or anything like that, which, honestly, if they included that, that would be pretty fun. Okay, the next few are all a bit more about kinematics, so if you've heard that word before, essentially it means using kinetic energy, movement, using SUVAT, you're using momentum. So the first thing you need to do is Newton's third law. Newton's third law just states that any action has an equal and opposite reaction. Now, just defining it, it's not good enough. There are times where you have to use Newton's third law in order to explain things, and by explaining things you need to make very, very concise and precise links. So what is Newton's third law actually? Well, it states that every action has an equal and opposite reaction. Yeah, okay, cool. What that means is, in this box example, this box is pushing down on the floor. Now the equal and opposite reaction is that the floor then pushes back up on the box with an equal force, but in the other direction. Now what you need to know is that they're also the same type of force. Okay, so this is really important when you come on to do things like circular motion and further mechanics. Conservation of linear momentum. Pretty important one. Basically, the sum of momentum should always equal 0. Okay? Momentum before is equal to momentum afterwards. This will come up again and again and again and again and again. Momentum is never lost. It's just moved into other objects. So be really clear on that. So you have things like collisions. Now here's again where people get these wrong. Personally, I think momentum questions are really, really easy and they're 3 marks a lot of the time. And a lot of the time they'll give you 5 or 6 marks and you only have to do 2 lines of working out. So why do they give you that many? Well, it's because every single year, lots and lots of students get it wrong. Why? Because momentum is a vector. Okay? The velocity, so if you have 2 things coming together, their velocities should have different signs. Likewise, if they're moving in the same direction, they have the same sign. A lot of the times, when students work out this collision, they'll take to the right as positive, but then they'll change direction in the answer, right? Which is wrong, lose marks. Or they'll make the velocities the same sign, or they'll change the signs, or they'll do some other weird stuff. You need to make sure you're consistent. This is why drawing a diagram is the most fundamentally positive thing you can do to increase your grade in physics and maths. Okay? This happens in A-level maths as well, because this is basically the same thing. You just draw a diagram, draw an arrow saying which side is positive, and then stick to it. Even if it seems weird, even if it looks wrong, stick to it and look at your answer and see if that's wrong. Because yes, there are some weird mathematical things, right? Like negative acceleration, even though it's falling downwards, where you think, well, it's speeding up, how can it be negative? It's because of the direction, that's all. It's still correct, okay? So again, drawing diagrams is so important. So I would recommend that you do a lot of practice with these mechanics questions in maths and in physics. So if you run out of physics questions and you don't do maths, get some maths ones, because guess what? All of this comes up, except for obviously conservation of momentum. That's it. That's the only thing that doesn't, and conservation of energy. Okay, everything else, like resultant forces, Newton's laws, come up in mechanics. So please use that as a revision resource. Next thing is use the concept of centre of gravity of an extended body and apply the principle of moments to an extended body in equilibrium. So, not sure about that, then again, videos on screen, hopefully. So, centre of gravity just means that if we have a big object, again, I use a box because I can't draw, then where do the forces actually act from, right? Like, do they act from bottom left, top right, or whatever? Well, the centre of gravity is basically where gravity appears to act, which is normally in the middle of an object. So the reason why I put air quotes is, if it's uniform density, which means the weight at the mass at every single point is the same, then it would be in the middle. But the thing is, if you think about real life objects like a human being, their density changes as you go to different parts of their body. That's why I put it in air quotes. Again, that doesn't come up very much. There are non-uniform bodies that you might deal with, but it's not too bad. But yeah, we have a centre of mass. That's where all of the forces are going to be acting from or to. Keep that in mind. And it also means that the weight will act from that point. Okay. Apply the principle of moments to an extended body in equilibrium. So what that means is, again, I'm kind of giving it away, but the moments is very important. It means the sum, that's what that sigma sign stands for, of moments clockwise should equal the sum of moments anti-clockwise. I promise my handwriting isn't this bad always. And lastly, we have used the concept of conservation of energy. So again, the total energy is constant. Now, the key thing here is total energy. Okay? So, for example, some people say, what about elastic collisions and inelastic ones? Elastic ones, kinetic energy is conserved. Inelastic, kinetic energy isn't conserved. Does that mean that energy isn't conserved? No. Total energy. So add up all of the kinetic energies, all of the potential energies, all the gravitational energies, add them all up and they'll always stay the same. So yeah, I've left the videos, again, you can skip through. I'm going to put chapters in the actual video, so you can skip to whatever part you need. The annotations are on screen for every single video that you might want, but again, just go back to wherever you may need to, words. And yeah, hopefully this is useful to you. Make sure you go through and just label it red, green and amber. What I mean by that is red is you haven't covered it, you don't know what it is at all. Amber is you may need some help on some exam practice, and then green is you're completely fine. And watch the videos for any that you are amber or red for, and I hope to see you in the next one.